Hi there, I'm Heath Ryanemi. I'm here with Mark Lindsay, and we're talking about VLAN tagging, the invisible layer that keeps your network from falling apart or causes it to. How we doing today, Mark?
We're good. So VLAN tags are a tag that carries more weight than you think. So here's the reality is that often, especially after you've done maintenance, you've added a new feature, you've added some new equipment to your network or a new virtual machine. Many network outages can be traced to and voice quality problems can be traced to misconfigured or missing VLAN tags. And it's often pretty hard to find. It's not going to be the things that were easy to test that get misconfigured. It's going to be the things that were hard to test. The background activity, the remote management network, the backup VLAN, things like that. And nobody notices until something breaks badly. So what Heath and I are doing is not a beginner tutorial. We're going to talk about why VLAN tagging matters at the systems level, especially for critical infrastructure, which is where ECG is focused.
All right, awesome. So, can you explain what a VLAN is and why we use VLANs in a switched network?
So to think about a VLAN, the concept behind that term, virtual LAN, we need to rewind a little bit to the old days when the word LAN was often used synonymously with just a hub or a switch. So that means you'd have this device, it's got 32 ports on it maybe, and that device is the LAN. So everything plugged into it is the LAN. So the concept is, well, I need a separate LAN for something else. I've got my manufacturing side, my industrial side, and then I've got my accounting department. And I've got these two. So the natural thing to do would be to buy two different Ethernet switches or two different hubs. Well, then people started thinking, well, what if I could just use one piece of equipment and I could use them all? I could put certain of these ports, maybe ports 1 through 16 on the accounting department side, and then 17 through 32 on the industrial side, and I could keep them separate. Well, that's the origin of the VLAN ID, the VLAN concept, is that you've got your switching functions, your hub function, basically split up inside the Ethernet switch. Now, where VLANs show up and VLAN ID show up is when we start to combine traffic onto the same cable, and we'll talk more about that in a few minutes.
All right. Well, how would you describe a VLAN to someone who only knows everything is just on the same switch?
A VLAN has to do with not just that the traffic is flowing through the switch, part might be true. VLAN has to do with what other devices it can talk to. So, two devices that need to be able to talk to each other in an Ethernet layer would need to be in the same broadcast domain with each other. And that means, in particular, that they need to be able to send packets to each other at the Ethernet layer. Technically, that means that when one of them transmits a MAC address as the destination in an Ethernet frame, and it translates that MAC address to be the destination of, let's say, another router, then that router is going to be able to receive that frame because it's within the same network, within the same broadcast domain. Or if a device transmits, say, a broadcast to like find the IP address of another device, let's say through the ARP protocol, that the broadcast domain is going to allow traffic to go to all those things. So the point of that is to say, if I've got my industrial side and my accounting side, and I've split them out, then those accounting PCs are only really going to be able to talk to themselves and other devices on that. They're not going to be able to talk to this industrial equipment. And that may be exactly what I want. But that may live inside the same Ethernet switch. So yes, the traffic may be inside the same switch, but it might actually be going to different places, and the VLAN defines restrictions on where the traffic can go.
Okay, so essentially, the VLANs it's all on the same switch, but the VLANs allow you to, in a way, create separate rooms for specific traffic to go in and not let other traffic go in. So the traffic can only go to certain places, but it is all flowing through the same switch.
Yeah, that's right.
Okay. Why do network engineers say VLANs create separate broadcast domains?
Well, the broadcast domain idea is the idea that you need to be able to send a broadcast packet, such as an ARP who has, which is the packet that says, I've got an IP address and I want to know what the corresponding Ethernet MAC address is for that, the ARP who has. So it's able to transmit that out. And we need to define where that goes. Now, obviously, if your smartphone transmits an ARP request for Wi-Fi, you don't really want that flooded to the whole world, right? You need to like limit it. Like it really only makes any sense like on your local Wi-Fi network. And Wi-Fi is functionally Ethernet for most purposes. So we need that to be limited there. The same thing would happen on an Ethernet network where you've got different machines. They're sending out broadcasts to each other. We really need to confine the zone where that goes. We don't want to flood it everywhere. One of the reasons is because of efficiency. Every time there's a broadcast frame that's sent out on the Ethernet, every device on that network or Wi-Fi network has to wake up, listen to it, analyze it, and determine whether this is a frame that they need to pay attention to. So broadcasts actually require work of everybody else in the network. And not that long ago, this used to be a major issue in network design, is you would have all these devices on a LAN, and they're sending out broadcasts, just ordinary broadcast traffic, nothing wrong with that. It's just broadcast to kind of discover what's on the network. And that would go to hundreds or thousands of other devices, which all had to wake up and slow down for a second and process this broadcast frame to determine what to do. And that's one of the, that type of segmentation is one of the things VLANs were applied to, was to help limit the size of broadcast domains. But functionally, a broadcast domain is a really convenient way to just to say, it's all of the Ethernet ports that my broadcast frame would go out to. And VLANs help me define that. So a VLAN and a broadcast domain is often used to be the same thing. So we define a VLAN to limit what their broadcast domain is. What we're going to talk a little bit more about in tagging is how we can get this traffic to other Ethernet switches.
So if we're sticking with the same theories, kind of the different rooms in the same house, essentially the broadcast domains by VLANs creating separate broadcast domains. If I walk in, if that traffic walks into that house full of sleeping devices, instead of screaming and shouting so that everyone in that house wakes up, it limits who that broadcast can wake up, so that you don't have every device receiving that cry for who's here and where are you at.
Yeah, that's fair. I mean, you could say it's like you're walking into a dark bedroom, you're sharing it with some other people, you got friends over, they're sleeping on the floor, and you want to know where everybody is so you don't step on anybody. You know, you don't need to wake up the whole house, but you might need to wake up that room. And so the broadcast gives you a way to talk to just the people that need to hear it.
That awesome. Well, let's talk about what VLAN tagging actually does at the wire level.
Yeah, so the core mechanics here are defined in a standard called 802.1q. It's something defined by the IEEE, which is an international engineering organization. And there's a 4-byte tag that has, among those 4 bytes, which are 32 bits long, 12 of those bits are a VLAN ID. And we're allowed to have VLANs numbering from 1 to 4094. And so basically that tells us the range of VLAN IDs that we can have. This tag, because it's stuck on a particular Ethernet frame, it should be easy for you to identify that it's associated with each Ethernet frame itself. So when an Ethernet frame is sent by your server into the Ethernet switch, it can put a tag on that frame to say, hey, Ethernet switch, this packet is related to VLAN ID 2. And then this next one that I'm sending is related to VLAN ID 4. And for most intents and purposes, that's functionally the same as having 2 cables that go in, one that's designated to a VLAN 2 port, and another that's designated to a VLAN 4 port. The Ethernet switch is able to receive that and identify, like, oh, this is intended to live in the VLAN 2 broadcast domain, and this one's intended to live in the VLAN 4 broadcast domain. Now, commonly, you're going to hear people say the VLANs are kind of a security boundary. And I used the example a minute ago of, 2 different departments, engineering and accounting, and they have traffic, and we don't really want the traffic to go between the two. But they're only useful as a security boundary in very narrow circumstances. They're primarily a segmentation tool. Something called VLAN hopping, which is where you have a port that allows you to specify your VLAN ID. And instead of sending the VLAN they thought you were going to use, you actually use a different VLAN. That's a pretty common exploit. So you can imagine you walk into a public place, there's an Ethernet port on the wall, or maybe there's a phone plugged in, and you unplug that phone, and that phone is set up for VLAN tagging because it's got a voice VLAN, it's got the regular PC VLAN. Well, what if you plug in a device in there, and you start listening to traffic? Well, you're actually going to pick up all the broadcast traffic coming in from that port. You're going to pick up all the VLAN IDs, and so you can discover all the VLANs that are available on that physical port. And that kind of attack is actually, unfortunately, pretty common among bad actors. They're going to use that to get access because network managers are not always limiting which ports can use which VLAN, so they're not narrowing it down quite well enough. This kind of thing has been exploited in industrial control systems and hospital systems, unfortunately, and it requires, that particular attack requires having some control over a device that's physically plugged into that network. So you can't do this per se across the internet remotely, but if you exploit and you get remote access to one of the devices on that network, let's say it's a phone, and you're able to take over remote access to that phone, and then you can send out traffic, then you may be able to launch a VLAN hopping attack. The relationship between VLANs and IP subnets, it's not necessarily one-to-one, but normally it's pretty close. So we would often have one VLAN, let's say VLAN 2, with an IP address block. Let's say it's 10.0.0.0/27. So it's a block of 32 IP addresses. And we would say, well, those IP addresses live inside VLAN 2. It doesn't have to be one-to-one exactly. And the reason for that is that you can technically put other subnets inside that same VLAN, and they won't really interfere with each other. Architecturally, we would often consider that messy. There may be some cases where it just makes things really difficult. But you can have one VLAN that's got multiple subnets inside of it. However, if you have one subnet, 0/27, and you want to like split it across two VLANs, that's a lot harder to do. And in fact, it's not even meaningful why you would do that kind of thing in most cases. You might have a VLAN that's you're using in a particular way, and you have a subnet, and I need to split the traffic up in some other way. But if you're using IP, then you're probably going to have two separate subnets on those two separate networks. Now, just because I say it's architecturally messy and people are usually going to avoid it and it's going to make your life terrible, doesn't mean you won't be able to configure it. There's a lot of crazy configuration that you can do in Ethernet switches and in routers. And so you're probably going to be able to configure this exact thing, even though it's going to make your life terrible.
All right. So knowing and understanding how important VLAN tagging is, and but keeping it clean in the process is what you're saying. It's important. It's a very powerful tool to help keep things secure and safe. But at the same time, it's very important that you keep it clean and well organized, since you said typically it's the one-to-one ratio. So, what does VLAN tagging actually mean at the Ethernet frame level?
Yeah, so it's really just a number. You could think of it as just the number of the VLAN is inserted at the beginning of the Ethernet frame. So when the Ethernet switch or the router or the server receives that tagged frame, it can identify which VLAN context it's intended for. And that's important because that device needs to know, am I dealing with, this particular logical domain or that one? VLANs can be used for it's sort of married up with MPLS, where you could have multiple customer networks. And so we may say, well, VLAN 2 is customer 2 and VLAN 3 is customer 3, and we really don't want their traffic commingled. And so we need that number to know which is which. Now, VLANs operate, I should point out, VLANs operate in a trusted connection scenario. So we fundamentally need to be able to trust the other devices on the other end. So if you have an Ethernet port that's open to potential access by a bad actor, then you would not trust the VLAN ID as it comes in. You'd have to do something else. You'd have to authenticate it, or you'd have to limit it and say, well, this port is only useful for this one situation. And that's often the reason why at demarcation points, let's say you're in a data center and you provide an Ethernet port to a customer for internet access, you may not put a VLAN tag on that because you don't want to depend on them necessarily tagging it in the right way. Or if you do put VLAN tags on it, so you set up as a trunk port so that it can accept VLAN tags, you're only going to allow them to send traffic on the ports, on the VLANs that they're allowed to use. So you wouldn't let it be generally open. But even in that case, you have to trust them to choose the right VLAN for the right situation. So it's a trusted scenario. Basically, there's no authentication. There's no authorization mechanism to use a particular VLAN, but it's just a number on the frame. That's really what it boils down to. It's just a number on the frame. If you take a packet capture and you encode the 802.1q tagging in that packet capture, then you're going to be able to see that number really easily.
Oh, well, speaking of 802.1q, what is an 802.1q header, and what problem does it solve?
Well, it's a good question. So the original Ethernet header didn't have any mechanism for VLAN ID on there. It also didn't have any mechanism on there for priority to say, well, this Ethernet frame needs to be prioritized above those. So it didn't have any of that stuff built in. So the 802.1q header is this extra 4 bytes that are added at the beginning of an Ethernet frame that says that provides this additional information. It makes the frame just a little bit bigger, and both sides of the cable need to be set up to expect that, oh, they're going to be sending me 802.1q headers. Now, you can also set up ports. Sometimes it's called native ports, where basically if I receive a frame and I'm a native port and it does not have a VLAN tag on it, I'm going to interpret it one way. But if it does have a VLAN tag on it, I'm going to interpret it and use that VLAN tag. So you can do that kind of thing. That's often a good transitional step. It's kind of messy to leave it in place. Sometimes you just have to do that. But it's really there to provide that information about what the VLAN tag is for this particular Ethernet frame itself. And it's important to remember that it's on a frame by frame basis. It's not like you set up the tagging and then all the future traffic is going through that. It's not, you're not dialing in a channel on the TV and all of your traffic is coming from that channel now. You're actually specifying on a per packet basis, which means you're going to be configuring your equipment that's transmitting there to both use 802.1q headers because it's not the default, and you're going to be configuring them which VLAN tag to use.
All right. Um, how do VLAN IDs in configuration relate to what's happening on the wire?
So the VLAN IDs in the configuration is talking about the idea that in your Ethernet switch, you're going to have different VLAN IDs that are present and then a lot that are not. So remember, we can have 4,094 different VLAN IDs on a particular port. And so in our configuration, we define that VLAN 2 is associated with the accounting department, VLAN 3 is associated with the engineering department, VLAN 4 is the manufacturing, industrial department. And so we put that configuration in, and then the VLAN ID that's in the configuration is the one that we're going to use to transmit the traffic out. So that determines the ID value that's going to be put into the packet that actually gets transmitted out. And then the other way, when a packet comes in, it's looking at that to figure out which one it is. Generally, what's happening is when the frame comes in, it's looking at the ID, it's identifying which VLAN it's a part of, and then it switches over internally logically. An Ethernet switch then goes to another table to figure out, okay, within the context of this VLAN ID, what are the available MAC addresses? Where do I need to go next?
Earlier, you mentioned that subnets and VLANs typically go line up one to one. But so what's the relationship between VLANs and IP subnets, and do they always map one to one? I know we touched on this a little bit more, but could you elaborate a little bit more?
Yeah, so remember in Ethernet networking, we can use a concept of layers. So layer one is the physical layer, just how we transmit the bits, how we encode the actual headers. So that could be photons in a fiber optic network. It could be electrons, signaling. Layer two is the Ethernet layer. It's where we have things like MAC addresses. And then layer three is the IP layer. It's the place where we have IP addresses. So this question is talking about what's the interaction between layer two VLANs and layer three IP subnets. To use your metaphor that you used earlier on, if VLANs are kind of a room, you could have everybody in the room with a green shirt and everybody in the room with a gray shirt. And all of us gray shirt people like me and you, we would be talking to each other at IP level. But the people with the green shirt, they'd be talking to each other at IP level. And we can all be in the same room. And when we send a broadcast, now if I send a broadcast, the green shirt people get it too. If they send one, I get it, all the from a green shirt person, it comes to me because I'm in the same room with them. But we're able to do communication there. So we can put together multiple, shirt colors, which is to say IP subnets in the metaphor. We can put them together in the same VLAN room, and they can continue to work kind of okay. That's often considered a little bit of a messy way to do things. You'd often prefer to minimize and control the traffic. And exactly what the downsides are is going to differ. Sometimes it's just a matter of, it's just a little harder to troubleshoot. They definitely don't always map one-to-one, but when you're designing something new, usually you'd have one-to-one. So if you have a subnet, you usually would define a new VLAN ID for that subnet.
So some of that has to do with security as well, right? Earlier you had mentioned if someone had gotten a hold of like in healthcare, an access to an IP and was able to broadcast. So if you're sharing that one subnet between multiple people, and one of it could maybe have more sensitive information on it. So say the green shirts are a department that handles a lot more patient sensitive material, and the gray shirts are just your regular receptionists or whatever. By broadcasting, they now can figure out who everyone is and the IPs for each of those. Is that a correct way to think about that? So it just exposes any potential threat to more devices if you do that.
Yeah, it depends on the kind of threat, though. I mean, the exact scenario of where the threat is really matters in that scenario. So you'd have to dig in more and more details to see precisely what it is. If the threat is at the Ethernet layer, then yeah, then generally speaking, having more devices accessed by that threat actor is bad.
Yep. So, what is 8021Q, and how is it different from the older Cisco IL or ISL?
Yeah, so Cisco ISL was a proprietary way of trying to accomplish some of the same things. Cisco's actually pretty good about this. When they see that there's a problem, they'll make an answer to the problem, but then when a standard comes along, they'll generally support the standard as well. So ISL stands for Interswitch Link. It was a Cisco way of basically connecting through Ethernet switches, and the concept would be if I've got VLAN 2 and 3 over here and VLAN 2 and 3 over here, and I want to connect between the two, then how do I maintain VLAN 2 traffic here becomes VLAN 2 traffic over here on my two different Ethernet switches. Um, it was a legacy standard. It's kind of deprecated. Cisco doesn't even generally expect people are going to use it anymore. It only supported about 1,000 VLANs. It was pretty big. The encapsulation on it was pretty big. So, like I said, the Cisco people, they go back and they participate with an organization like the IEEE to define a standard for how to do it. The Cisco method probably, I think it had some other data in it that was in addition to 802.1q's headers number. So it had some other stuff in there. Cisco's ISL only works on Cisco devices, so you can't buy a Juniper switch and add it to that and get the advantage of that. But 802.1q is generally the standard that's used for defining this header format, and particularly like the way that we declare that a particular packet belongs to a particular VLAN.
And so 8012 kind of became more of the industry standard because of how more universal it was. You could use it across multiple devices instead of being locked into Cisco specific devices.
Right.
Okay. So how does 8012Q tagging actually embed the VLAN ID into the frame?
So the 802.1q tagging, and if you say that 1,000 times, then it'll be easy to say. It'll roll off the tongue on the 1,000th time. 802.1q tagging, it really takes the Ethernet frame intact and then just inserts these extra 4 bytes at the beginning. And basically, there's something in there that says at the beginning of the frame that says, "Hey, I'm going to have an 802.1q tag now." And then it puts that in there, and then the rest of the frame is in there. So if you're in a switch implementer, the Ethernet switches need to know how to process this. If you're looking at a Wireshark, you'll see the 802.1q right at the very top.
Well, let's move on to access ports versus trunk ports, the distinction everyone thinks they know.
Yeah, so this is something everyone feels like they're comfortable with when they're not always comfortable with it. So access ports strip and add tags invisibly. And what that means is if you think of the traffic inside the Ethernet switch as being tagged internally, and it functionally is, and when it comes in, it's assigned to a VLAN, then basically that's what's happening. So the access port, when you send an Ethernet frame into an access port, you expect that it doesn't have a VLAN tag on it. There's no 802.1q tag. Whereas trunk ports actually carry the tag frame for the multiple VLANs simultaneously. So the trunk port is expecting that when frames come in, it's going to have an 802.1q tag on it. Native VLANs are sometimes called the silent killer. So the native VLAN, kind of what's the default VLAN if I didn't have any tagging? And sometimes one of the common misconfigurations is you'll get an Ethernet switch, you'll change the passwords, and then you'll leave the default native VLAN as VLAN 1. And then you go about your business, and at some point, some device over here is transmitting an access traffic on port VLAN 2, and it comes in over here, and it gets remapped over to VLAN 1 in a different switch. So the VLAN 1 and the use of native ports is often a problem. It's kind of widely discouraged. It's just too easy to make mistakes with it. There's something called dynamic trunking protocol, and by default on many Cisco switches, its goal is to automatically configure which VLANs need to be available. But it is really a known attack vector. There are ways if an attacker has access to an Ethernet port, like the example I gave. You walk into a building, a hospital, and there's a port, and it's got a phone plugged into it. Well, if you can plug in and you can emulate DTP, then you might be able to configure that remote Ethernet switch to trust you. And it's because functionally Ethernet ports are not always connected to trustworthy devices. So what devices connect to what port types? one of the key things is that access devices are generally any device that's not going to be adding an 802.1q tag, or they don't need access to multiple VLANs at all. Whereas most servers, especially in a virtualized server environment, most physical servers, some routers, they're going to need to be able to specify a VLAN tag. And so engineers will get this wrong by using trunk ports or access ports in the wrong places. Generally speaking, a rule of thumb at a lot of organizations is that they're going to use .1q trunked ports between all the infrastructure equipment, and then customer endpoint equipment is going to use an access port.
Yeah. Um, so to kind of help clarify some of that too, can you explain what the difference between an access port and a trunk port is?
Yeah, so an access port does not ever send an 802.1q tag, which means that it has a VLAN identified with it. So when each frame comes in, it recognizes that frame as belonging to a particular VLAN, and then it processes in the switch internally like that. On the other direction, whenever the frame is going out, if it's a frame, let's say it's VLAN 2, and it's going out through a port that's assigned to VLAN 2, but it's an access port, then the Ethernet switch does not add a VLAN tag to it. A trunk port, on the other hand, is looking for that information to come in on the tag. So if it belongs to VLAN 2, it has to say VLAN 2 on the frame. The frame has to have the 802.1q header on it for the trunk port to recognize it. Even if that's the only VLAN that's assigned to the particular port, if it's a trunk port and it only allows VLAN 2, the tag still has to say it belongs to VLAN 2.
Okay. When would you configure a switch port as an access instead of a trunk?
Strictly speaking, it's when the device on the other end doesn't know how to do VLAN tagging. But heuristically, kind of the rule of thumb is often that access devices, customer access devices, endpoint devices, that those are going to be untagged. And they're just going to be assigned to a VLAN. They're not going to have an option of specifying which VLAN. Another way of saying it would be ports where we don't really trust the other end of the connection. Like the other end of the connection is a device that it could have an attacker on it. We don't really trust it, and so we're going to confine it to one VLAN. We're going to ensure that it only stays in one VLAN.
What does an access port do with VLAN tags when frames come in and go out?
Well, there really are no VLAN tags on an access port that are going to get recognized. So normally, if a tagged frame comes into the cable on an access port, then the Ethernet switch is going to just discard that frame. It's not even going to necessarily even count as a frame. It may not increment the counter. It may increment an error counter if you look at the statistics in it. And then when they're going out, there's no VLAN tag put on it either. I think probably what some people are thinking of with a question like this, what does an access port do with the VLAN tags, is that internally in the Ethernet switch, there's functionally an Ethernet VLAN tag. Basically, as traffic moves between ports, it's basically assigned to a VLAN tag so that the switch internally is able to recognize which VLAN it's on. And that would be true even if it's an Ethernet switch which only has one VLAN defined. Maybe it's saying fresh out of the box, it's VLAN tag, VLAN ID 1, that's the default. It's going to tag the traffic internally will be identified as VLAN 1, but on an access port, it's never going to actually transmit the VLAN 1.
Mhm. Um, sorry. What does a trunk port do differently from an access port on the same switch? So if you have a trunk port and an access port on the same switch, what does it do differently?
Yeah, what's different there is that the trunk port is identifying the VLAN based on that VLAN tag that's coming in, and then it is providing that frame to the correct VLAN internally on the Ethernet switch. And then when frames are going out through the trunk port, it's actually the switch is adding that VLAN tag to the frame and then transmitting it out so that it's identifying which it is. On the very same switch, an access port is going to be assigned to exactly one VLAN at a time. And so it's not going to have the ability to do that, process those incoming VLAN tags, or transmit the VLAN tags out.
All right, so we talked some about being one-to-one earlier, but can a trunk port carry more than one VLAN, and how? So does the VLANs, do trunk ports need to be one-to-one with VLANs, similar to what we had discussed earlier with subnets?
No, they don't need to be one to one. So a trunk port can definitely carry more than one VLAN, and the way you do that is by configuring the Ethernet switch to allow multiple VLANs on that trunk port, and then uh, you can allow traffic for all of those to flow through that trunk port. So, for example, let's say we have VLANs 2, 3, and 4. Those are defined. You can set up a trunk port to allow all 2, 3, and 4, or just one of those VLANs or two of those VLANs, and it's only going to allow that traffic to come inbound. So, if you have it configured to allow VLANs 2 and 3, and an Ethernet frame comes in with VLAN tag 4, then it's going to drop that frame. It's not going to be processed and go through. And then similarly, if you've got in the other direction, traffic for VLAN 4 would never go outbound through that trunk port. So a common activity is when you're adding a new VLAN for a new situation, then you have to enable the VLAN traffic to flow. You have to allow that on the port. Now, by default, I will say a lot of Ethernet switches will allow all VLANs on all trunk ports by default. And generally, engineers will often discourage that. They really don't want traffic flowing willy-nilly through the network. They want to define which VLANs are allowed to go across which cables. And so we would normally put an allow list in to allow certain traffic to flow through certain ports.
What is a native VLAN on a trunk, and how does traffic for that VLAN look on the wire?
So a native VLAN would be the VLAN that is effectively assumed if there is no VLAN tag. So the concept there is that you would have maybe a VLAN trunking capable port, but we're going to define a native VLAN. So if a frame happens to show up and it doesn't have a tag on it, then we'll still recognize what it is. This can be a useful transitional step. So you might, let's say you're adding VLAN tagging, you've got a switch plugged into a server, and we want to enable VLAN tagging. Well, let's say that server was on VLAN 2 already. But we need to log into that server to reconfigure it for .1Q. So we could configure the switch to use native VLAN 2 on that port. We can enable VLAN tagging so it's able to send traffic, but anytime a frame is going to or from VLAN 2, it's going to leave it untagged at the, for the moment. And then we go over to the server. We log into it remotely. We make a similar change. We set it up as a native VLAN. So we enable VLAN tagging, but we leave VLAN 2 as untagged. And then what we have to do is make a switch at some point where we set it VLAN 2 to tagged on both sides. There are ways to do that, but it depends on the operating system. But usually you've got to get your timing, your sequence right. What's easiest to do is if you've got another VLAN, you could log into the server through a different VLAN in effect. Let's say VLAN 3, a different IP address. You can log in through that. That's tagged now. And then I can reconfigure it to remove the native VLAN. So I remove the dependency on the untagged traffic. And then we can remove the native configuration. So we could effectively use the native VLAN as a transitional process.
Okay, and as we said earlier, though, the native VLAN is something that you typically don't want to leave in place long term.
Yeah, I think not. It's a little harder to predict what you're going to get on the port. There may be scenarios where it is a good long-term permanent solution, but generally speaking, if the port is connected to a device that's able to do VLAN tagging, then you want to do a VLAN tagging. If you trust it, if the port is not trustworthy, if you don't trust what's on the other end of the port to send you an accurate VLAN tag, then you probably don't want to turn tagging on. So having a VLAN tag on there where you've got the ability to send untagged traffic and at the same time to tag traffic, it seems questionable.
Okay. So speaking of different devices that, we talked a little bit about what to expect from the device you connect to. What kind of devices do you typically connect to access ports versus trunk ports? And what would be the reason for specific devices on those ports?
Yeah, the often it's customer endpoint devices that are not capable of VLAN tagging. So if you go to a Marriott brand hotel here in the U.S., they usually have Ethernet ports in many of the rooms, and you can plug in your laptop to the Ethernet port, so you don't have to actually use the Wi-Fi. They actually get some government business because of that, because a lot of government agencies are not allowed to use Wi-Fi. They have to use actual physical ports to plug into the local hotel network. So for that case, they're not going to tell you, hey, you need to go configure your computer with a VLAN tag before you can get a DHCP-based IP address. They're just going to give you an untagged access port. So that would be a classic example of it's not a trustworthy device. It's a device that just needs to get, in this case, internet access, and it doesn't have the ability to do tagging. And so that would be a good example of that kind of scenario. But even if you're building an enterprise network, you've got devices, you do trust them, You may have devices that you're never going to expect to send multiple VLANs, and so we could configure that to be just one port. So, for example, a printer, it might be 802.1q capable, but we really just need our printer to be on exactly one network all the time, and so we might define that as an access port for that printer.
Okay, can you give an example of a real world link that should be a trunk and what VLANs it might carry?
Yes, a phone, a SIP phone, a VoIP phone would be a good example of a device that, even though it's an endpoint device, probably should be a trunk because typically VoIP phones have an Ethernet switch capability themselves. So they have a PC port. The idea is that you would bring your PC, you plug it into the back of your phone, so you have that port, and then the phone has a voice VLAN, and VoIP VLAN would be tag traffic, but also the PC port is tag traffic. So when the phone is connected to that trunk port, it's able to tag the voice traffic and also the PC traffic separately. Another example would be a virtualized server host. So let's say you've got a server, you've got a bunch of customer virtual machines on it, and they're on 25 different VLANs. Then you're going to need to tag that traffic so that the switch knows which traffic belongs to which VLAN coming from which server on that machine. So scenarios like that would be really common where you've got a need for both ends of the cable to identify traffic on different VLANs.
Well, thank you so much, Mark, for taking the time to speak with us more in depth on VLAN tagging and how that can help just help your network and keep it from falling apart, and helping us also kind of discuss some of the issues where improper tagging could actually cause some issues. So I thank you for taking the time and digging deeper into those topics with me today.
Thanks very much, Heath. I appreciate the opportunity.
You have a great day.